To show up in that monitor. Welcome to our hangout with the Cornell Astronomer team. This is our second Alumni Affairs Google Hangout, so thanks for joining us on this Wednesday evening. And today we have a group of guys from the Hill who know an awful lot about space. And so they're going to answer any and all questions you have with regards to the cosmos. If we have to dip into some life advice, maybe we can do that, but that's going to be up to them. So I'm going to let them go around the table and introduce themselves and let you get to know them a little bit, and then we'll jump right into the Q&A. Now, if you have a question for our Ask an Astronomer team, just type it right into the chat box that you should see underneath the viewing screen. And we will do our best to get it to our experts here. So, without further ado, I introduce Carl, Jason, Sean, and Michael. And Michael, why don't we start with you?
Sure. Hi, I'm Michael M. I'm a third-year grad student. I work with Jim Cortez on pulsar timing. So we use pulsars, which are these very compact objects which rotate extremely rapidly, and we time them like precision clocks. And we use those clocks as measures of tests of different physics. And so particularly I look at properties of the interstellar medium, the gas that permeates between the stars of our galaxy.
Sounds simple enough. That's great.
Hi, I'm Sean Marshall. I'm also a third-year grad student in astronomy. I work with Professor Don Campbell, focusing on studies of near-Earth asteroids as observed in the radar and infrared. So a lot of the stuff I'm working on right now involves basically trying to figure out, people often assume that these are spherical when they're first discovered to estimate their size and other properties. So I'm trying to figure out, if you assume it's a sphere and it's not, like, how bad is that? How much will that mess you up? So yeah, yay asteroids.
Great.
Hello, my name is Jason Hofgartner. I am yet another third-year astronomy grad student at Cornell. I am working on my thesis studying Saturn's largest moon, Titan, studying both the interior of Titan and the surface. And Titan is an extremely fascinating body because, in particular, for many reasons, but in particular because recently liquid lakes of both methane and ethane have been discovered on the surface of Titan. And that makes Titan the only body aside from Earth to have stable liquids at its surface. So it presents a lot of opportunities for studying liquids at a planetary surface in a different sort of context.
And I'm the old one at the table. I'm in my 7th year actually as a grad student at Cornell. I'm finishing up this semester, and then hopefully I'll be going to a postdoc over in Germany. But in the meantime, for my thesis, I do submillimeter astronomy. So it's very similar to the sort of work that CCAP will be doing, that Cornell is working on building. So I build a camera and a spectrometer, put on a telescope in the Atacama Desert, and I went there and observed. I used that then to look at galaxies and try and understand how galaxies form and build up their stars in the early universe.
Great. Well, I think we certainly have a wide breadth of knowledge here with regards to astronomy. And again, I'll just remind everyone, if you're just joining us and you want to ask a question to our panel of astronomy experts here from Cornell, just type it in the chat box and we will get it to them and read it on your behalf. So let's start out, guys. Just if one of you want to just talk about kind of what are the cool and interesting things happening within the walls of Cornell astronomy right now.
CCAP.
Well, yeah, I mean, I think a lot of the big excitement is involved with CCAT. Actually, right now, this week, there's this big design review going on for the CCAT telescope, where they're having this external panel of scientists come in and basically look over the designs and stuff. But I think there's a lot of excitement involved with that, but there's a lot of other really great, exciting things going on. So, like, also on the second floor, which is where I'm on. The Professor Terry Herder, he's got an instrument that's been flying on the Sophia spacecraft, and they just had an observing run with it last week. And so they take it. There's this basically there's a telescope built into a side of a 747, and then they go and fly that up in the atmosphere to look at infrared radiation that would normally be absorbed by atmosphere, the water in their atmosphere, and they're able to study and learn things about the dust around the center of the Milky Way. So that's some of the cool stuff.
Yeah, there's a lot of Cassini research here in the planetary group. Many astronomers focus on Cassini. Cassini is the largest satellite that has ever been sent into the outer solar system, really to any other planet. And there are astronomers at Cornell here working on using it to study Saturn's rings in particular, a big group for that. There are also several folks here studying Saturn's largest moon, Titan, using the Cassini spacecraft, and as well as the rest of the Saturnian system and the other satellites of Saturn. So Cassini is a very big mission, first one ever to go into orbit of Saturn with many, many discoveries, and Cornell is one of the hotspots in that mission.
Great. Let's talk a little bit more about the CCAP project, because I know that's become quite a bit of focus within our operation. Actually, it's kind of being spearheaded by Freddie Young from the class of '64, who's invested a lot of time and financial resources into making it a reality. Jason, could you talk a little bit more about the specifics of the project if no one has ever heard of CCAP before? Could you kind of?
Well, I'd actually might be a better one to explain. My thesis advisor, Professor Gordon Stacy, is actually one of the the scientists that's working on designing actually one of the cameras for it. So yeah, so the idea with CCAT is Cornell and a collaboration of a few other universities, including Caltech, University of Colorado, Canada, and stuff. The goal is they want to build a 25-meter telescope that will be sensitive to light that is shorter than 1 millimeter. And then they're going to put this telescope on a really, really high mountain in the Atacama Desert in Chile. It'll be about 18,500 feet. And the whole point of doing this is those wavelengths of light, those we call them sub-millimeter radiation, the water vapor in our atmosphere absorbs them. And so if you tried to make those same observations here in Ithaca, you couldn't. None of the light in sub-millimeter wavelengths makes it to the ground here in Ithaca. There's so much water vapor. And in fact, so if you took all the water vapor above us here in Ithaca and you condensed it down, you'd get a pile of about 6 inches of water. In order to observe at these wavelengths, you actually can only have 6 millimeters of water or less. Actually, ideally, you'd want about 1 millimeter of water. And there's only a few places on Earth that can do this. The Atacama Desert in Chile is one of them, where we're going to hopefully put CCAT. And of course, maybe one of the questions is, why do we want to look at these wavelengths? Well, a couple reasons. One, these wavelengths of light is the wavelengths that dust emits out in the solar system in galaxies. And so, where optical light is really probing stars, a lot of the light that a star actually emits gets absorbed by dust, and then the dust re-emits it in the millimeter wavelengths. And so if we want to understand where the dust is and the gases in the universe, we need to really look at these wavelengths. And then the second one is because the universe is expanding, wavelengths of light that we would normally study in optical and infrared here in our galaxy or nearby, if we really want to understand the galaxies early in the universe, we have to go to longer wavelengths, because the expansion of the universe redshifts it. It shifts those wavelengths to longer wavelengths. In CCAT, it's basically what it's going to do for the sub-millimeter. It's just going to do really huge surveys. And so where if you can think about in the optical, we have Hubble, which does really high resolution things. It really looks at really hot things, at images in high detail, but not over a large section of the sky. To get the large section of the sky in the optical, we have projects like the Sloan Digital Sky Survey, which are basically just looking at a third of the sky, just trying to count numbers of galaxies. Well, in the sub-millimeter now, CCAT's going to be the big survey telescope, like Sloan Digital Sky Survey, to really count the number of galaxies and identify and find interesting galaxies to look for. And then right next to CCAT, there's this thing called ALMA, the Atacama Large Millimeter Array, and that will then be able to zoom in on the things that CCAT finds and study those in detail. So CCAT is, to really leverage the awesomeness of ALMA, we need a telescope like CCAT, and Cornell is leading the community, the astronomy community, to get that. So it's really exciting.
And this is really an opportunity for Cornell students to really step in and become major leaders in the industry, correct?
Yeah, I mean, so one of the goals for CCAP is to be a platform where students can learn about building telescopes and instruments and things like that. And so, having Cornell involved with that, it means that students will be able to get involved in the process. In the lab I work in right now, Professor Gordon Stacy's lab, there's obviously grad students do a lot of work, but we have at any one time we have 2 or 3 undergraduates also working, building up the components that eventually get put into a camera. So having access to a telescope like this and getting it built provides a really great opportunity to actually learn hands-on how do you actually go about making the technology to study the universe.
Well, I know there's a lot of work that needs to be done. I think there's still about $13.5 million that needs to be raised. So if anyone's out there and wants to help support this project, contact Cornell Astronomy for more information about the CCAP project. So we have our first question coming in from the chat room, so I won't waste any time jumping in there. And it comes from QQW, who wants to know, what are the parameters of the term universe? Where does that term become inapplicable?
I've talked a lot.
I can do it. Okay. Well, I would say that the universe encompasses everything that we know, and I realize that that's a very broad thing to say. Pretty much, we can know about what we have observed in the universe, and we can go back that far. So if you take the beginning of the universe as the Big Bang, a lot of people have many misconceptions as to what the Big Bang means and what that implies for the universe. The Big Bang itself was the start of our universe. It was the start of both space and time. So there was nothing that we know of that science can say that came before the Big Bang, before our universe. Similarly, a lot of people ask the question, what is outside of our universe? Because they sort of envision, here's our universe, and there's a boundary, and then beyond that there's, something else. Really, there's nothing else. It's not that there's empty space. It's not that there's a vacuum. It's that there's nothing. There is no space beyond that of the universe. So when we talk about the universe, we're talking about something that is everything that we know and everything that we can observe. As for the parameters of the universe, I guess it depends who you would ask. Cosmologists would give you a couple of parameters. I guess broadly you'd say something like, what is the age of the universe? And that we've measured to be about 13.8 billion years. People can ask, what is the size of the universe? And that's something like 40-something billion light years in size. And it depends on the models and how the cosmologists work things out, but I would say those are probably broadly the so-called parameters of the universe.
Yeah, I would say probably another thing that we know along with that is how much stuff is in the universe. So astronomers, scientists, cosmologists, we like to say matter and energy. They can be switched between each other. So we actually have a measure of what the total energy in the universe should be. And we can break that up into different components. So most of the energy in this universe is actually a lot of stuff that a lot of people probably heard of called dark energy. That's like 75% of the universe. Then the other 25% is what is matter. But of the other 25% that's matter, only 4% of it is the things that make up you and me, the stars and the planets. And what's really interesting, and I think this is really interesting, is if we went 15 years ago, this whole idea of dark energy, nobody in astronomy would have been talking about it. So it's been this really neat, interesting, some great measurements that prove that dark energy exists, and they've been the evidence is so strong that basically we had this huge paradigm shift in the field of astronomy and physics and cosmology and how we actually view and understand our universe. So it's really cool.
Do you guys have like a hard time sleeping at night with all of this knowledge swimming around in your head? I mean, I can't even imagine trying to, contemplate these things. I mean, I'll stare up at the sky and be like, where does it start? Where does it end? What's going on up there? And you guys seem to have a lot of those answers. I don't know if that would make me more settled or thirsty for more knowledge, but that's impressive nonetheless.
We're graduate students, so we don't get sleep. So it's okay.
Well, I'm a father of a 2-year-old, so we're about even there. At least you're doing it for the case of science. So I guess that a lot of that brings me to a question. Then we'll jump back into the chat because another question just popped up. But you hear people talk about the price tag associated with a operation like NASA, right? So what is the argument for why space still matters to America? Yeah, we beat the Russians to the moon. That was great. But what answers are out there that really can legitimately help us with regards to life on Earth?
So that's always a really good question. I mean, NASA does spend a fair bit of money, and it's important to ask why we're doing that. And there are a lot of different reasons or ways to answer that question. So I can elaborate on a few. One of them that comes to mind right now, just because it's very pertinent recently, is exploration, and in particular, unexpected exploration. So just last week, scientists formally announced that the Voyager 1 spacecraft, which was a spacecraft launched by NASA in, I don't remember the exact year, but in the late 1970s, to go and study the Jupiter and then Saturn. And that spacecraft was very successful. It was turned a huge amount of knowledge on Jupiter and Saturn. And then for the next 30 years, it's just been cruising along still, further and further from the sun. And just last week, scientists announced that they're certain now that spacecraft has left the solar system. And that is that was something that was discussed in the media, but really probably wasn't discussed or realized to the extent of just how important that is. Because that is, to me, that is essentially as important a step almost in the history of humanity as, say, Christopher Columbus reaching the New World, or Neil Armstrong landing on the moon, because this is the first time that we've ever gone beyond the solar system. And sometimes in the media we don't catch on to that as much if it's not a person, it's just a robot who's done this, because we can't relate to it as much. But that robot has left the solar system, and the solar system is this amazingly well-suited place for us for our life, and we're so used to it, but it's really nothing at all in comparison to the greater universe. And so there's a huge step that people can still take, and a lot to learn about the universe every time we go somewhere new. That's one of the basic lessons of exploration, is every time you go somewhere new, you learn something. And this is an example where NASA has gotten somewhere new before any other country, before anyone else ever has. And they're learning about what's out there beyond our solar system now in the whole wide universe. And this is something that Voyager 1 and Voyager 2, it cost a fair bit of money at the time when it was launched, and it learned a lot of successful things from Jupiter and Saturn. And then it has been kept alive on not too really much of a budget at all. And yet now it's extremely important and has a very, very historical. And that serves. It's gonna. I mean, it's just such a big step. It's going to give us so much knowledge that we can learn from, and we can grow from that. And as far as the price tag goes, NASA's budget as related to the whole budget. I don't remember the exact number, but it's less than 1%. It's something like 0.7%.
Well, maybe if Miley Cyrus could cool it, we could have more astronomy on the front page of the news. But I think that's a great point. I mean, that's something probably most people don't realize, and to put it in a historical context like that of exploration and what all the famous explorers did to sail around the world and things like that, and discover the geography we now take for granted. I think that really says it. And actually, the second question that came in from Andrew, he said Voyager 1 just moved into interstellar space, and he wants to know what it's like there. Probably warmer than Ithaca.
Well, so that the Voyager thing for me is actually another thing that's interesting, because also it seems like over the last 15 years, about once a year there would be an article saying Voyager 1 has left the solar system. So there, there's kind of an interesting impact there in looking at the social aspect of science. Is, when do we as a group of scientists, when is the consensus saying that we are actually, we can actually agree on something? And the most recent article, as Jason pointed out, is finally it seems everybody that's involved with Voyager 1 has agreed. And what's really interesting, is, okay, we're outside the solar system, so I think there's a really, as you pointed out, this great impact. But what is it really different out there? Not a whole lot different. The big difference is, one thing we like to say is, are you in the solar system or outside the solar system? Is are you being influenced by our sun? So is there a solar wind? Is the magnetic field from the sun? Are you being affected by that? Or are you being affected by the radiation and the magnetic fields that exist just spread out through the galaxy? And so that's really the only difference. And the exact details of what that looks like, I think, the details are exactly coming in, because Voyager 1, it's just, finally said we're just out there, outside the influence of our sun. So it'll be interesting to find out, as Voyager keeps traveling, what more details they can come up with.
Great. Well, we have another question. Somebody was asking about your specific research areas, which you explained a little bit when you introduced yourself, and this person has admitted to and maybe have missed that, but they were also curious, kind of, what does your research areas, what is the impact on, let me say this verbatim, what impact does potential learning have on ordinary people? I guess ordinary people are those of us without the capacity to understand what it is you guys are doing. Maybe to try to clarify that. I guess people not in astronomy. So, as I said, what is the case for science, or what is the case for astronomy in terms of how it benefits life on Earth? I think that's...
Yeah, so I wanted to, along those lines, I'll admit, my actual research, myself trying to understand why galaxies formed and how they formed 10 billion years ago, is not going to ever affect anybody's everyday life or an ordinary person. I will admit that. But as Jason pointed out, there's a sense of exploration, of trying to figure out the unknown. Long time, Cornell Astronomer Carl Sagan, said something along the lines of, as humanity, we have the ability to reflect back on the universe in we're this clump of matter that can actually look back and reflect and try and understand the universe. So we should do that. But I think in my specific work in this trying to always understand the unknown, we actually drive technology, which does have an impact. So some of the biggest, newest projects in astronomy, like CCAP, these are really challenging technological problems that nobody else in society is trying to develop the technology to do. And so we are driving new technology, which does have an impact on what we do.
Yeah, NASA has this long list on their website of technology that's come out of the space program, and people talk about Tang. That's not the only thing. They've got medical monitors, better solar panels, thermal blankets, a whole host of other stuff. Because they get that question a lot, and it's an important question. So
yeah, so I think the technology, one of the new, what's really cool, I think, is one of the new projects. I keep saying what's really cool. I think astronomy is really cool.
I would hope so. You're not sleeping.
Yeah, I'm doing it, right? Yeah. There's this project called the Large Synoptic Survey Telescope, and their basic goal is to take a picture of almost the entire sky every single night. So from night to night, you can look at changes of what's going on in the night sky, and they're going to produce so much data that we need new databases, new computers. And so Microsoft and Google, they've actually signed on to help with this project, because it's something that, there's so much data, and we want to be able to study it and ask questions about the data we found, and there's no current way in computer science to do this. And so, as databases of Facebook and Google and all those things get larger and larger, having the technology and new databases available, that's going to be something astronomy is going to be able to give back to the broader technology community, which is kind of cool.
Well, and you could probably also point to things like pixel rate, which used to be I know is important in telescopes, and now we all kind of take for granted how good our smartphones are.
Yeah, yep, absolutely. Yeah.
So,
there's a lot of things we can add, like just to keep on the idea of technology, and a lot of times it can be the technology that's driven for astronomy, but then is inadvertently extremely useful in some other aspect. And there's countless examples, but one of my favorite ones, I think that strikes say deep is seatbelts actually. So seatbelts are directly relevant to what was happening with the space program and the Air Force program back in the I believe the 50s and 60s. This was a time before rockets, and America was actually progressing on a space program that would have put people in space using balloons, very, very high altitude balloons. And because of those balloons that would have come down quickly through the atmosphere and struck the surface of the Earth quickly, high G-forces, a lot of acceleration, that was known that would happen. People were studying how to protect those astronauts. And at the time it was considered, well, humans just can't survive that sort of acceleration. We're only meant to survive the acceleration that we experience from gravity. Much higher would kill us. And there were studies done that people could in fact survive huge accelerations up to 20, 30 times as much as gravity, with some bruising, some effects, but basically altogether perfectly healthy. And it was basically a direct result of that discovery that people decided to put seatbelts in cars, because before that it was thought, well, if you have a really serious accident, you're not going to survive it anyway. And that's not directly related to the space program, but that's an example of something that is related to the space program, and it's inadvertent technology. And how many of us are alive today or have loved ones alive today because of seatbelts?
Yeah, that's a good point, and I think all the NASCAR fans owe you a bit of gratitude as well. Otherwise, we probably wouldn't have that sport to look forward to. So we have another question that came in from QQW. He wants to know, they want to know, what's the greatest unsolved mystery in astronomy that you can think of?
Dark energy?
Probably dark energy.
Yeah, probably.
So Carl was talking about this thing, dark energy, and it's we know that it exists because we know that the expansion of the universe is accelerating. So not only is the universe getting bigger, but it's getting bigger at a faster rate. So we know, and we can figure out how much energy is involved with that. We really have no idea what dark energy is. We don't know what it's made of. We don't know, I mean, is it something that permeates space? Is it a particle? I mean, we really just have no idea. We know it exists. We know it's out there. We know it's 3/4 of the total energy content of the universe. But yeah, we don't really know. Can't get a handle on it.
I would actually say another one, which it's not really an unsolved mystery because we know it's got to be out there, but the discovery hasn't happened yet. We don't actually have the direct evidence. Would be an Earth-like planet around another star. We know there's, in the last, since I became a grad student, really, our understanding and the number of planets, exoplanets detected has grown astronomically, and so we have a really good sense of statistically how many planets are there out there, how many stars have planets, etc. So we know there's got to be a planet with that's in the habitable zone, in the region where we have liquid water. There's going to be one that's close to Earth size. We just we haven't found that one yet, and then we haven't made the direct image of it. And technology is getting better. More and more observations are happening, so it's going to happen. It's just a matter of when, which will be cool.
Yeah, so with regards to that, I think that's probably one of the top questions the general public has with regards to astronomy, with regards to, is there another Earth-like planet out there, and is there other life out there? Let me ask you this, and this might be kind of a hot-button question. Where does the world of astronomy, do you see any areas where your discoveries could directly clash with some of the more traditional philosophies of life on Earth, different religions, things of that nature.
Who wants to take that one?
So,
I didn't stump the astronomers, did I?
so I'll try it. Certainly, astronomy. So as our stated goal, and this is an answer that will vary hugely depending on every person that you ask. But our job basically, as astronomers, at least to start, is not to sort of get too much into the philosophy or the theology, that sort of thing, how these implications affect that. Our job is to stick to hard science, where basically we follow the scientific method. So we're proposing hypotheses, things to explain the universe, and then we're making observations to see that those hypotheses are right. And as Carl started the conversation here, one of the major ones that we have is that we've had for a very long time was that there are plenty of planets around other stars. In fact, there should be planets around many, many stars. And before I was born, it wasn't known. People debated about that all the time, whether it took very specific conditions to form planets, or they should be very abundant. And astronomers have gone and proven now that there are thousands, there are many, many, many planets out there around other stars, and all kinds of unique systems, some that somewhat resemble our own, some that are very, very different. And there's a big push now to find a planet that resembles Earth, and it won't be long until we're capable of that detection. Whether or not we find one remains to be determined. Our statistics are suggesting to us it's going to happen, and we're expecting to be capable of it. And that's what astronomers really focus on. That's sort of our bread and butter job, is to do that. And then there are varying degrees of branching out there to go after the philosophy and theology. And the results of our studies is also a very personal dependent thing, so that each person is going to respond to them differently, and it's going to affect their own philosophy and theology as well.
Also, I'd like to just mention, basically, as scientists, we are really not out to crush people's dreams. I think the goal of science, according to Richard Feynman, Nobel-winning physicist who was at Cornell early in his career, in one of his books he mentions basically the universe follows certain rules. There's certain things that can happen, certain things that can't happen, and we can basically do experiments, make observations, try to figure this out. The goal of science is figure out the rules of the game, as he put it.
Well said.
Feynman was very good at explaining stuff, so yeah. He's mine.
No, I just kind of bring it up because sometimes I wonder if maybe you guys, in your field don't get as much credit as maybe you deserve, or as much attention as you deserve, because people are, a lot of people might be afraid of what you discover. And I don't know if that ever kind of hamstrings your operation, or that causes more scrutiny than probably is deserved with regards to scrutinizing budgets or things like that. So yeah, I guess that's just one thing I personally am always curious of. So we can again, if you're in our chat, feel free to start sending in some more questions for us. We got about probably 15 minutes or so left of hanging out with our Cornell Astronomy team. So if there's anything at all that you're wondering about with regards to space and astronomy and anything in that nature, go ahead and type it in the chat. So I recently, well, you know what? Let's talk. Let's have a little bit of fun with some of these space-related questions. So, what is your? Let's go around the table and tell us what and why. What is your favorite space-related motion picture, and why?
So many. There are a lot. Oh.
I'll start. Star Trek II, The Wrath of Khan, with the Genesis device. Just think it's a great story. Khan's a great villain, sort of makes the movie. Just basically have a good story, good villain. Genesis device is a really interesting idea, for something they can create rather than destroy, but it has the potential to be used as a weapon. So, just think, great space-related movie. There's my vote.
Some say the best of the series.
Yeah, I agree.
Ricardo Montalban.
Yeah.
Rich Corinthian. Nope. Did I just not date myself? Well, actually, for me, there's a movie called Solaris. It's like this really old. There's an old version of it. I think it's actually like Russian or something. And it's like really, really long, like 3 hours. Not that version. There's a newer version that stars George Clooney, and I just really, really like it. There's just it's really great, cinematography, really well put together, but it really, it's kind of more on a philosophical level, questioning, what actually, raising questions about what we actually know, like when we see something and when we observe something, what is it that we actually are actually seeing? Can we know something? Is there some truth out there that's concrete? So that's mine.
Good. I don't know. That's a tough one.
Didn't we answer this?
Yeah, I don't remember what I picked last time. There's too many.
We get this question a lot.
Well, since you've already taken Star Trek 2,
Galaxy Quest.
That's Galaxy Quest. Thank you. Because
Tim
Galaxy
Allen?
Quest is a parody of me. And so I get everything because I am the guy who goes to conventions and dresses up and may or may not keep uniforms in his office. So, yeah, Galaxy Quest is thank you. I approve.
Yeah. Yeah, I'm sorry. I'm going to have to stick to the good old original Star Wars trilogy. Love that one. Yeah, definitely a big impact on me.
All right. Well, we have another question that came in from one of our viewers in the chat. And it's a rosy, optimistic type question, and it's how will the universe end? Will it be a big crunch, a big rip? What will happen?
So I think the current belief, now that we've observed this thing called dark energy, now that we see that the universe is expanding and the expansion is accelerating, is that it will end very, very, very cold and very, very, very dark. Kind of depressing, but that's the way it seems like it's going to go.
Kind of like a fizzle, a firecracker that just kind of.
Yeah. Yeah.
Or more poetically, not with a bang, but a whimper.
Yeah. So pretty much, since
Ice, not
everything is moving apart from each other, everything is moving apart from each other, but locally gravity attracts. Thank you. Gravity attracts things so that against this outward expansion, and so depending on how strong dark energy is, maybe clusters of galaxies may stay together. Maybe individual galaxies may stay together. If dark energy is really strong, stars themselves will be sort of ripped apart and then spread very, very far from each other. So all of the light that we see out there could end up going away and getting very redshifted and also just physically far away from us. So it will end up very, very, very dark. And yeah, because the universe is getting bigger and since there's the same energy, it will end up very, very cold. And so, yeah, it is kind of depressing. It is a bit of a whimper.
But on the other hand, when does this happen?
When does this happen? I don't know.
Billions of
100 billion years?
No, I think it's like 40 billion years.
Yeah.
Well, in that case, I better get my affairs in order.
Yeah. Yeah. Nothing to worry about.
Sounds like it's for Cornellians. They can just think of it as a January walk up live slope, dark and cold and uncomfortable. So somebody just in the chat. I'm not familiar with this movie, but somebody wants to know if you're excited for Ender's Game.
Yes.
Okay, I love the book. I hope the movie is faithful to the book, because sometimes Hollywood has issues with taking a good story and sort of ruining it. On the other hand, some turn out very well, so we'll see.
But it's got Harrison Ford in it. It's gotta be good.
Hopefully. Look, I hope you're right.
It'll be good. Orson Scott Card, the author, is like a creative director or whatever on the movie, so it'll be good.
Well, there you have it. It will be good.
Guarantees.
I don't know the premise. What's the premise of the book?
Earth was about to be wiped out, and then
By hostile aliens.
yeah, now they recruit young kids as their generals.
Try to like develop a different kind of mind that's capable of like winning against the aliens, basically. But yeah.
So that brings up a fair question, right? What are the odds that, one, we will discover other life out there, and two, will it in fact be as hostile as Hollywood seems to portray it as more times than not?
I'll take a shot at this.
Sure.
Okay, so will we discover life out there? I think realistically this will happen in stages, maybe during our lifetimes, maybe not. So the first step, as Carl sort of mentioned, is try to find some planet that we'd consider Earth-like, that's in the right part of its solar system, something where you expect liquid water can exist, which is essential for life as we know it, and maybe there's other kinds of life, but start with what we know. Okay, so find a planet in the right place. Then try to find something with, try to actually measure its atmosphere, figure out what's in there, see if there's signs of life there, like molecular oxygen. Then maybe you find some signs of like plant life, plant activity, photosynthesis, something like that. Maybe we have to go through several planets like that until we can finally get one where somehow we get some hint of intelligent life, or maybe not. But keep in mind these are probably like hundreds of light years away or more, so it's hard. Basically, we can't really communicate with them during our lifetimes. And as far as like hostile alien invasions, I'm sort of skeptical of that from a scientific standpoint, because it would take so much energy just to like get to our solar system that I'm not sure how much they gain from like actually trying to conquer it, other than like trying to colonize some other uninhabited nearby system. Also, on the subject of books we like, one of my favorites is called The Mote in God's Eye by Larry Niven and Jerry Cornell, which is like really good, I think, description of like contact with an alien species, which are very different from humans. It sort of enforces the idea that hopefully they're friendly, but we shouldn't assume that. Anyway, good book. Look it up.
Yeah, I was going to say along those lines is, yeah, okay, so what I'm going to say is not astronomy, but I say, looking at our own world and how difficult we have having a society and communicating with people that have very different experiences. We have issues of race and culture and things like that. And now try to imagine doing that with an actual different alien species that grew up and evolved on a completely different planet than us. So I think, is there intelligent life out there? Maybe. Will we run into it? Maybe. What's going to happen when we do? I have no idea. It's going to be interesting.
Yeah, considering we can't even seem to get along on our own planet, I wonder if an alien species would even be all that interested in kind of extending an olive branch in our direction. That was going to take me in another direction, but that escapes me now. So, speaking of which, so it seems like you've kind of hinted at this a little bit with regards to looking for another Earth and things of that nature. So, what do you think will be the next, of all these things maybe that we've discussed tonight, what will be the next great achievement or discovery for astronomy? Or what has the best chance of being
the future is notoriously difficult. I do think we'll get Earth-like exoplanets soon. Again, like seeing their atmosphere or seeing signs of life, that may be decades off, but we're finding some. Well, there are already a couple that are thought to be in what we call the habitable zone that are close to Earth size, so that's probably not too far off. I don't know, cosmology stuff.
Direct detection of gravity wave. So there's been Einstein's theory of general relativity predicts that accelerating mass, just like an electron, an accelerating charge emits electromagnetic waves light, that if you have an accelerating mass, that should be giving off gravitational waves. And there's been several observations, one of them being orbiting pulsars that you're able to measure that, yes, they're emitting they're emitting gravitational waves, but we've never actually measured with any sort of detector yet a gravitational wave. And so there's a bunch of projects, including this thing called LIGO, which is these really sensitive, really huge sensitive instruments in a couple places all over the world that are trying to detect them. And then actually Michael's work is a bit involved with trying to find gravitational waves too.
Yeah. So I guess I'll clarify one point, is that the gravitational waves, they're like what you might imagine as ripples in space-time. So if you imagine like you hold a fabric and you put some balls onto it, you can see that the fabric deforms, and that's kind of like the waves and things like that Carl was describing. The original so-and-so detection was actually an indirect detection. So we didn't see any gravitational waves. We see that the orbit is changing, and we predict a certain change from general relativity, and those happen to match. So we haven't actually directly observed gravitational waves, and there's a few projects. LIGO is one where you're using this 3 to 4 mile long laser bouncing between mirrors, and you're trying to measure how space changes over 3 to 4 miles. And it's actually, they're measuring something to within the width of a proton. So about 1/100000th, like the width of a human hair, something around there. So pretty difficult measurement, which is why I haven't done it. My work, which using pulsar timing, it's got the same idea, except instead of having 3 or 4 miles, you have 1,000 light years. And so you're trying to measure differences in when pulses from these pulsars arrive at your detector. And the differences have to be, they're on the order of nanoseconds, which is a small amount, but not unreasonably small. I mean, it's bad in the sense that we haven't done it yet, because it's a very difficult measurement. But these are currently the two key projects working to detect gravitational waves. And so if we can detect gravitational waves, for thousands of years, primarily astronomy has been electromagnetic waves. There's been a couple of other things. We've been able to see neutrinos recently, but pretty much light in some form. Maybe it was optical photons, maybe X-rays, maybe radio photons. But if we can start to see the universe from a gravitational point of view, I mean, then you're really opening up kind of a new window into what we can see, what we can observe. And so that's going to be pretty exciting, I think. I think that the Earth-like planet will come first, though. But we're hoping within the next few years to make a direct detection and go from there.
Well, I wish you the best of luck in that. It sounds like a pretty fine measurement, but we trust you're up to the task. So we have another question coming in from, and I might pronounce this incorrectly, their question from Retug. Where are the missing baryons? Does that make sense?
Baryons.
Baryons.
Yep.
Do we have an idea where those missing baryons are?
So I can take this.
Could you maybe define baryons for the people in our audience, like myself, that clearly are not familiar with them?
Yeah, so baryons is basically matter. It's the stuff. It's protons and neutrons. It's atoms. It's elements. It's the stuff you and I are made of, and it goes into the baryons. We know, well, the baryons fall into that 4% of what the universe is made up of. And there's this problem is that if we go out and, as Michael was saying, that astronomy, until we can detect a gravitational wave, we detect light. Now, of course, light's emitted by baryons, by matter. And so, astronomers, we like to go, we'll look at a galaxy and we'll say, okay, we see all this light. and we say we can estimate then how much matter must be there to emit that amount of light. And when we do that, we don't get enough. We essentially, we try and add up all the light we detect and say, okay, this should be this much matter, but it doesn't equal the amount of matter that things like the cosmic microwave background should say. It doesn't add up to the 4%. And so where is it? Well, likely it's there. We just can't see it. In order for matter to emit, it's got to get energized somehow. It's either got to collide together, so it's got to have some temperature, it's got to be warm, another photon energy has to come in and hit it, and if that doesn't happen, we won't see it. And so, our assumption, we can only see matter that really is in a galaxy, or excited by a huge galaxy. And what we're actually starting to see is we're starting to see evidence that there's a lot of matter actually that isn't in a galaxy, that's still primordial gas that might be left over from the universe form that hasn't fallen into a galaxy yet. So we just can't see this stuff, and it's there. We just need to do a better job of actually looking for it. One of the questions, so that's where the missing baryon problem is now. Originally, one of the problems was also that is what actually came up with this stuff called dark matter. And that is, if you look at a galaxy and how it rotates, you would basically expect as you move out from the center of a galaxy, the stars and the solar systems that are orbiting around the galaxy, you would expect them, the speed with which they're orbiting in the galaxy, to slow down. But measurements, what they actually saw is it would flatten out, it would plateau. So basically, where we are in the Milky Way, we're moving at work. We're very far from the center of the Milky Way galaxy, but if you went out twice as far out to another star that's twice as far out from the center of the Milky Way galaxy, they're orbiting at the same speed. That was weird, and the only way to explain that is if we invoke this stuff called dark matter, some other stuff, some other matter that we can't see. And that dark matter, though, it's not normal baryons. We don't know, some of it could be. But we know from observations of the cosmic microwave there has to be some exotic particle there. And actually, the Large Hadron Collider might start giving us hints about what subatomic particle that could be. And there's a few other experiments. There's this one called AMS. It's something magnetic, alpha magnetic spectrometer or something like that. It's this huge magnet that they launched up as one of the last things brought up by the space shuttle, and it's on the International Space Station. And basically what they're looking for is if there's this particle, this exotic particle that makes up dark matter, that particle might decay into something else. And so one of the ways to detect dark matter, which normally wouldn't interact with light, which would be hard to detect, would be to detect the things that dark matter decays into. So there was actually a recent paper on some of the first data from AMS, putting limits on what the dark matter particle could be. So we don't really know. But
well, hopefully that was an answer that Retug can digest.
Probably more than the person expected.
Hey, that's what we're doing this for. So we're just about out of time, guys, so thanks everyone for submitting questions and for tuning in. And I just want to end with this question, and you guys can kind of quickly go around the table. And that is, if you could have one astronomy-related question or mystery answered tomorrow, something that's really bugging you or that you're just dying to know the answer to, what would it be? What's the one thing, if you had to choose one?
So I'll give those guys a second to think about that. For me, I think hands down, my biggest question that I want to know is, will humans ever live on other planets and within the cosmos? It's not. I don't think it's an obvious answer. There's an obvious answer to that at all. It depends on the choices we make, on what happens, and I think it'd be really interesting to see whether or not humans are sort of confined to planet Earth, or whether we choose to become a multi-planetary species.
So for me, it's not necessarily something specifically I want to know. and in general, I want to know more about these galaxies, what they were like in the early universe. But for me, it's more of if I could go out tomorrow and observe something, it would be I would observe a galaxy in the early universe with the Atacama Large Millimeter Array, which is one of the most, if not the most, groundbreaking astronomical instrument in the last, since Hubble, really. It's amazingly sensitive, and if I could have 24 hours to observe a galaxy with that, I could find out so much. So that's what I would do.
Well, if there's anybody out there watching that can make that happen, let's hook Carl up.
Yeah.
All right, I'll go. I guess so. Related to my research interests, basically, sort of a more obscure topic, but basically how microscopic structure on the surface of an asteroid affects the radiation field that we observe. So, basically, we have I work with thermal models. You can put in an asteroid, the shape, the size from radar observations, and also put in the thermal properties, compare that to the spectrum we observed, and then basically try to find the right combination of thermal properties, which tells you about composition, surface porosity, some other stuff. And one of the big questions with that is basically how exactly does really small structure, like microscopic bumps on the surface, affect the radiation field that gets to Earth, which we observe. So we have various ways to parameterize that. But I wish I had an asteroid up close that I could just go to town on and see what the surface looks like.
So you're supportive of Obama's mission to go collect an asteroid and bring it to Earth?
Well, I don't know. You'd have to do this in space. I have this vague idea. I'm not sure how exactly we do it.
I think Jerry Bruckheimer put together something like that, didn't he? Nobody said Armageddon was their favorite space movie. I'm shocked.
That's so good.
Wow. You didn't have to say that, Michael.
No, it's okay. I'll defend it. So I think for me, as much as my collaborators would probably want me to say, could I figure out how much gravitational waves emission is there out there in the universe? If I could get the answer to one thing, I would think it would be where is life out there? I think that's something that everyone has, at least in the back of their mind, and I don't do any research that deals with any part of that, but I think we just don't know, and I think it's very difficult to find out. Like we said before, I mean, even if we find it, can we communicate with it? Probably not. But if I could get the answer to it, tomorrow, I think that would be it.
Well, I think that's a question on everybody's mind, certainly, and I think we'd all look forward to maybe that discovery. It certainly would mix things up a little bit down here on Earth. Well, thank you guys so much for joining us. I think we could spend hours upon hours picking your brain and asking questions about what's going on above us, because it is, at least for me, and I'm not even in the science, I find it really fascinating, and I don't think it's talked about enough or really considered enough, considering we're as I think one of you said, such a small blip on the universe map. But thank you so much, and I hope maybe we can do this again and dive into some more topics. But in the meantime, for those of you watching, thank you for joining us for this second installment of Cornell Alumni Affairs Hangouts. Feel free to visit astro.cornell.edu to learn more about the Cornell astrology. That's very different, isn't it?
Whoa.
Cornell astronomy. Don't call.
It happens more than you think.
Don't call asking for your horoscope or for them to answer those questions for you. But look them up. They're doing some amazing stuff up there. Learn some more about the CCAP project, because I think that'll make all Cornellians really proud. That can get off the ground and look into ways that you can support what these guys are doing, because it's really impressive stuff, and they're definitely leaders in the industry, and they make Cornell proud, Cornellians proud, and are certainly a source of pride for the whole Big Red family. So thank you guys, and thank you all for tuning in, and we'll see you back here probably at more towards the end of October, we'll have another one of these for you. So thanks again, and we'll see you soon.